Testing sequential circuits. Okay, how does this look? Is it hard to see? Yeah, that's true. So we're looking at testing sequential circuits, and I was mentioning that one possible approach for testing sequential circuits would be to use the very same approach that is used for combinational circuits. That means you excite the fault and then propagate the fault in the outputs. And in case of a sequential circuit, it will take a few clock periods, because you need to apply test sequences. And the sequence in which you apply the patterns, so a test sequence is a sequence of patterns, and the sequence in which you apply these patterns, the behavior obviously would be different because the nature is sequential. Other approaches to change the problem to a combinational testing problem. Okay, how's this white?
It's better.
Yeah, white looks much better. Oh yeah, that green is kind of dark. That is true. Okay, so we put it back there. So as I was mentioning, one rather common approach in hardware. Now there is time to time I will mention about the similarities and differences between hardware and software. And one good thing about software is that it is very accessible. You can go in and you can probe inside very easily. In hardware, probing inside, that takes effort. So a lot of times for hardware testing, we assume input-output situation, that you don't have internal access. Now I was mentioning about the BIST approach. Now this works well when you have a combinational logic which is sandwiched between two registers. So this is the combinational logic. And we assume all the faults in the combinational logic. Now in the BIST approach, built-in self-test, this is a generator. This is often a pseudo-random pattern generator. And here is the signature analyzer. So you basically let the generator run for a while, and you compress the responses into a signature, and then you take a look at the signature and see if the signature is good. And if the signature is good, you can presume with very high degree of probability that it is actually a good circuit. Now there are situations when you have sequential circuits with feedback. And in that case, now the situation is like this. So you have the combinational circuit, and here you have a bunch of storage elements. Okay, then I'm going to modify this a little bit. So here are the state variables coming in, external inputs, external outputs, and let's assume that these are maybe rising edge triggered flip-flops or some suitable type of combination circuit. So here the question is, here is X, Y, and here is Z. Now last time, did I call these lines D lines? I think I called them D. So basically you need to test, so here basically the inputs to the combinational circuit are X and Y, and outputs of the combinational circuit are Z and D. Now you have here the problem of controllability and observability, and in fact these are terms that are used even in software. Why they are not? You don't have direct control, you have only indirect control. So you have to get it into the right state. So you need to be able to somehow control these Y lines, and somehow you need to be able to observe these D lines. These are of course coming out, so there's no problem in observing them. So the question is, if this is a sequential circuit, how can you do that? So people struggled with this problem for quite a while, and then they figured out that there is a clever way, and it is, this is in the general area of design for testability. Basically, make sure that the circuit, when you design it to be testable. And one design for testability scheme is using some kind of scan. And the idea is that provide some path so that these storage elements are controllable and observable. So, and the idea is that in the test mode, you can configure these flip-flops as a scan chain, and for example, you have this is what IBM came up with, etc. And here you have a scan out. So basically, you create a series path in the circuit so that you have in this scan design two modes. Let's try this part of the board. So basically, this circuit, so in this scan design, you have two modes. So you have the normal mode, and basically inputs, these inputs are coming in parallel and going out in parallel. So here, parallel in and out for the storage elements. And then in the test mode, basically they work in serial in and out. So one bit at a time, the bits will come in and go out. And the cost is going to be, you need an extra pin here, you need an extra pin here, and you need a pin for the mode control. So maybe 2 or 3 extra pins, and maybe 4, depending on how you implement it. But then you have a direct path to the storage elements. So that gives you controllability, and direct path to the output, and that gives you observability. So here's the sequence. So you scan in a vector in the test mode. And then you let the response in the normal mode. And then you scan the response out in the test mode. So, scan in some values, and now you have, these are of course externally controllable anyway, so now you have scanned these values in, and then let it run for one clock period. Output will be available here, and these are going to be latched here, and then you will scan it out, so you will be able to get the state variables out through the scan out path. And so basically now your problem is that of testing a combinational circuit, because these are directly controllable now and these are directly observable. So it's a problem of testing a combinational circuit. Now there are some issues. So your scan chain could be long. And one possibility is you can have multiple chains in the circuit. Remember, if you have, let us say, 100 flip-flops there, it is going to take you 100 clock cycles to scan in the 100 state variables, and it is going to take you 100 clock cycles to scan the values out, so that is going to take time. So one possibility is you divide that into a multiple scan chains, so you kind of scan them in parallel and take them out in parallel. Other possibility is, this is a term sometimes used, partial scan. Maybe you analyze the circuit and decide that a certain flip-flops, they are hardest to reach. So you only connect those flip-flops into a scan path, and you don't, and others you take care of it somehow. So this is termed partial scan. Now let us say if you are, this is about hardware of course, so this is a very popular approach, and there are several variations of scan technique, and there's a variation of scan which is called boundary scan. Sometimes you have a number of chips on this board, and the idea is that if you can test the behavior at the input-output pins of a chip, then you can exercise them to a considerable extent. Now we had seen a theorem which said that if it is a fan-out free circuit, then if you test all input pins were stuck at false, you would have tested all the false. In general, of course, that is not true. But still, if you test for all the input-output pins, you would have tested a significant part of the functionality. So in the boundary scan technique, they have all these chips on the board, and each of the chips, for each of the chips, all the pins are connected in form of a scan chain. So during the test mode, all these scan chains, they get connected, and so you can scan out values under some test conditions, and that is referred to as boundary scan. Now in case of software, now there is a software analog to this. Actually, we don't have our software expert today. But in software, you have these integrated development environments, but I guess most of you may have used it anyway because they are now very popular. For example, Eclipse and some of the others. And these will allow